Hi everyone, I want to share a model I made with you guys. So it comes from this source here, which I'll show the DOI of. So if you want the math behind it, here you go, source DOI here. Basically the paper looked at, am I recording? Okay, I am. Sorry, I didn't realize I was still recording. It didn't look like it. Basically what we're doing here is looking at what is the viscosity of a tenarary, which means a 3-component solvent system. What's the viscosity with different mass fractions of each? All right, I can plug in some mass fractions and then find what is going to be the expected viscosity. And basically, it's a very simple idea. It's just basically taking the individual viscosities and weighting them based off of data that the authors found. So I'm using this in an internship I'm doing, but something to add is that there's a correction for small amounts of alcohol, which is important to us, or any component. You just need to know the viscosity of it. So there's 3 parts I want to show you. The first part is this one here. So this first little bit here, what you're doing is you're plugging in mass fractions of each component that you have. So let's say you want to know, okay, what viscosity should I expect in this mixture that I have? Okay, so you put in your mass fraction of water, glycerin, PG, which is propylene glycol, and ethanol. You put in the temperature which your liquid will be measured at, and it outputs a simple value. And here's the scheme. It's nothing crazy. And this, don't worry about this. This is just some experimental data I took on my end. But basically, the interface pulls, or you plug in values here, and the computation is just pulling from that. It also finds it in kelvins. It finds these beta constants, which are important, and the weights of those beta constants, which is used in the final viscosity reading here. And here are some constant values that scale with temperature. That's important, so that's why the temperature component's there. And we also use some good viscosity finding formulas. That wasn't scientific at all, what just came out of my mouth, but you get the point. So that's what we're trying to find, and that is the first part. So let's say, for example, you have a 1-to-1-to-1. So if you can't really reach 1, you can just do like 0.33333. It should be good. So if you have a roughly 1-to-1-to-1 mixture, you're going to get 7.627 viscosity out. If I then add some ethanol, so let's say I drop the PG to 2333, how much would I need at that point? I'm sorry, I don't know the sum of these values. That's bad. So I need 0. Okay, I need 0.00. Why is this so hard for me? This should be 1.1, and then let me just increase the sum. Does that make sense? Screw it. I'm gonna make it easier on myself because I can't do simple math. Let's say we add some ethanol in there, and we're gonna say, okay, this is 20, and then this is 0.05. That balances out. That's a little easier. You can see now there's some difference in the uncorrected versus the corrected viscosity, and it reports that difference. So the more ethanol you add, the more deviation from the model you get. The calculation on the ethanol is not great. It's just a small correction if you have small amounts. This model does not assume the interactions that the ethanol has with the other components. So you got to keep that in mind. You can use up to like 0.1, but you really don't want to go any more than that. For example, you couldn't use 0.5. You can't have 50% of your mixture use ethanol when the model doesn't even consider the interactions of ethanol, right? So just important to keep in mind. But let's also consider the other part of this, which is a little more elaborate, a 3D graphing portion. And in 3D, what we can do, because we can't set all of these to independent variables, we can't say, okay, I want H2O to be an independent variable, glycerin to be an independent variable, and propylene glycol to be an independent variable, because the dependent variable is something you need to plot too. So you would get a 4-dimensional function, and that is impossible to actually show. I'm sure there's ways. I know physicists, have time in the 4th dimension, but I'm not that savvy on graphing those things. So we're going to stick with a 3D plot. And these models that I have here, 1 through 3, what they do is they set one of your mass fractions constant and you can see what happens as the others change. And the scheme for this, we'll just look at water. Basically, what happens here is I have a generated set of points given a constant mass frac of water. So let's say, for example, 0.25, 25% water. Basically, what it's going to do is the glycerin mass fraction is going to do 1 minus both the ethanol and the water, generate that point, and keep going down until we get to 0 minus all those points. And then PG is just 1 minus everything, right? That should make sense. And it generates a list of points, either viable or not, right? Notice how you can't have a negative % of something. So that's the negative check column. That's basically saying, okay, any negative points, just get rid of them, set them to 0. And then we also do this mass balance because sometimes you can get over a reasonable amount. For example, the 0.8 term here, well, 80% PG and 0.25 or 25% water, that doesn't make sense at all. So we avoid those terms as well using this mass balance check. And we're going to calculate subsequent beta values, which are listed in the paper, so check it out if you want to learn how to calculate those. We filter out any ones that give an error. That's just a simple if error command, and simply we just add weights then, and we filter out any value. And what we do is we do the ln weighting, so e to the sum of the beta times ln terms, and that's going to give us this viscosity, which I simply turn into centipoise, and we do a correction using that ethanol correction if any ethanol is present. And then what happens is we put it on a little report here saying, okay, here's everything you need to know. And then we take those viscosity values and we make a 3D plot. And if you know anything about linear algebra, you have to plot everything on the main diagonal if you look at this as kind of a matrix, right? Because all the other points are invalid points in the domain of this 3D plot, right? We can't have 0.35 and 0.05, but then only have 0.25 water. We would be missing percentages of just nothing, right? And that doesn't make much sense. So the only valid domain is such that all the values, including the constant, adds up to 0.1. And you can see, in fact, that's what this main diagonal does. And we just simply graph it. So that's what that's doing. And not only does it generate a contour plot, so you can look at a top-down eagle-eyes view, you can also look at the function, the parabola that it makes in 3D, right? So you can see the viscosity will maximize at one point, and it will usually always make a parabola when you're working with PG glycerin systems. And it's that's the interesting thing, and that's what we kind of found when we worked on working with these solvent systems, because you would assume, because glycerin is very viscous and propylene glycol is not very viscous, that you add more glycerin, it should, and drop the amount of propylene glycol, you would expect that you would increase your viscosity, but it turns out that a 1-to-1 mixture of PG and glycerin is ideal. So for example, let's say you were at 0.25 or 0.35 glycerin, 0.15 PG, right? You'd be somewhere like here, and your instinct would be add more glycerin, but you'd actually be going down the parabola, making your viscosity less when you wanted to increase it. So that's some like takeaways you can bring from these graphs. Interesting things are seen with like the glycerin and PG models. I wrote this wrong, that we set PG constant. And mass fractions of, that's fine, glycerin and water. Sorry, I didn't spell this right. You can see that we're maximizing as we add PG, because water and these viscous solvents, they don't necessarily interact the same way as glycerin and PG do. Glycerin and PG kind of work together, and they prefer to be in a one-to-one mixture. However, with H2O and these solvents, obviously, because the viscosity of water is very low, as you increase the mass fraction of either PG or glycerin, right, you're going to, and sorry, these graphs are wrong a little bit. As you increase the amount of PG or glycerin, you're going to massively increase the viscosity. We can see going from anywhere from 0 to 100 all the way to 300 to 400. Okay, so, and I should make a note of this. Here, I should probably change this. This is of glycerin. You can see it increases, and the function instead is like an exponential, but in 3 dimensions. But yeah, that's all I wanted to show. This is just a little thing I've been working on, so I thought maybe, it could help someone. If you find it cool, if you want the download to this, reach out to me. I will give you the file. That's fine. I'll put my email in the description. Feel free to send me an email if you want a copy. But anyways, that is a model for Tenarary mixtures of propylene glycol, glycerin, H2O, and small amounts of ethanol. Thank you. Have a good one. Bye-bye.